These are the colligative property notes. It will be helpful to have the pink formula sheet and a periodic table and calculator available as you complete these notes. As a reminder, we are talking about our unit on solutions, so just our vocab language of solutions. Our solute is what is getting dissolved. It is what you have less of. Our solvent is what is doing the dissolving. It is what you have more of. Often we have that as water, but we are going to talk about some other solvents today as we talk about other solutions and colligative properties. A solution then is a homogeneous combination of that solvent and solute. Homogeneous meaning it's going to be evenly distributed. And so we can take the solvent plus the solute plus the solvent. That's what's giving us our solution. So if we were making Kool-Aid or lemonade, our solvent would be the water, which is dissolving the solute, the powder, to get that Kool-Aid or lemonade mixture solution. So what happens when a solute dissolves? So we were talking about things dissolving. We've talked about aqueous solutions before and solubility. And so with these, we are talking about those soluble ionic solutes. And when a soluble ionic solute dissolves, it will dissociate or break up into ions when it is put in water. And so we aren't going to deal with anything that is not soluble. We are just talking about if it's a solute, it is going to dissolve. So an example would be sodium chloride is soluble. So it is going to split up into the sodium ions and the chlorine ions, so dissociating into two ions or two pieces. Something like lithium sulfate, which is soluble, would dissociate into two lithium ions, lithium plus one, and one sulfate ion. We saw this as we were doing our models, those solubility models, to show there's my lithium, and then that sulfate. So that's how we can see those three ions disassociating or breaking apart from each other in water. And we're going to come back to that a little bit later. There is another video, feel free to watch that as well. It also discusses how this applies to how colligative properties influence the chemistry of cars. And so what is a colligative property? Well, we've talked about properties in terms of chemical and physical properties, but we focused more so on chemical properties because those were then things that we could see chemical changes occurring. But we didn't talk a lot about physical properties. And physical properties can be divided into two categories. Extensive properties depend on the size of a sample. So like the mass of something or the volume of something. Those are dependent on the sample. That's often information we use for calculations. Intensive properties are characteristic properties of a substance. So they do not depend on the size of the sample that is being studied. So things like density or concentration don't depend on how much you have. You might have mass and volume to use in calculating a concentration, but the concentration is going to be the same throughout. You don't need that whole sample to determine those things. And a subset of intensive properties, so that don't depend on the size of a sample, are colligative properties. And colligative properties only apply to solutions. So we're not going to talk about colligative properties when we are looking at anything aside from a solution. And so what are the colligative properties? Colligative properties are properties of a solution that depend only on the number of particles dissolved in the solution, not on the identity of the dissolved particles. So we don't care if it's sodium chloride that's getting dissolved or lithium sulfate that's getting dissolved. We are going to care that sodium chloride breaks up into two ions. We're going to care that lithium sulfate breaks up into three ions. So we are going to be looking at the number of particles that are dissolved, not what those actual particles are. So that's kind of what it means by colligative properties. Examples of colligative properties are freezing point depression, boiling point elevation, the lowering of vapor pressure, which means that something is not going to evaporate as quickly, and osmotic pressure. And these two that are kind of starred here, we are not going to discuss these in detail. We'll talk about that lowering of vapor pressure and what it means a little bit, but we are going to mostly focus on that freezing point depression and boiling point elevation and those impacts with that. So you feel free to do more research on those ones if you want. We're going to focus on the freezing point depression and the boiling point elevation. Excuse me. Boiling point elevation in the boiling point elevation in the description of and the explanation of that property, it does talk about vapor pressure. So I'd want to just briefly talk about what does vapor pressure mean. So that would mean that something does not evaporate as quickly. How would we measure vapor pressure? Well, this diagram here is showing us that if we have something like pure water, even though this is in a liquid state, if we were to put this in an enclosed container and measure what is the pressure of the gas molecules as that is evaporating, or as those molecules are kind of breaking off from the top of the liquid, the pressure that we have there gets lowered if we are dissolving, this one is sodium chloride, if we have those sodium and chlorine ions in there, that vapor pressure is going to go down. And we can see that because those particles that get dissolved are now blocking other water molecules on the top, so less is able to turn into that water vapor in that enclosed container. So then less of those are hitting, and that is a lower pressure. So that is what it means by that lowering of vapor pressure. You just have to understand that basic idea. And then as we look at this, we do need to consider our states and phases of matter on a molecular level. Water molecules in solid ice are going to have bonds that are going to form that solid ice structure. Our water molecules in liquid water, those are going to be able to move around more and adapt to the container that they're in. They're not going to have a fixed shape. And then water molecules in water vapor or gas, those are going to have more energy and are going to not have a fixed shape or volume with that. And so as we're looking at talking about boiling point and freezing point, well, that freezing point is when you're going from liquid to solid. Boiling point is when you're going from that liquid to gas. So going between those phases. So let's discuss those first two that are going to be our focus. So first we're going to talk about freezing point depression. And so freezing point, the temperature that something freezes. Depression, that means something is going to go down. And so freezing point depression, how we're going to see this in our formula, delta T sub F, that F is for that freezing point. And we are talking about the temperature of the freezing point going down. And this says that the freezing point of a solution is lower than the freezing point of the pure solvent. So if we have water, which is a pure solvent, and it freezes, the colligative properties, or what we know, is that now if we have a solution, so if we have something that is dissolved, then that freezing point is going to go down. The salt is going to hinder the water molecules from forming ice crystals. And so that is going to change the freezing point for the solution. Why does this happen? Well, more energy needs to be removed from the solution to go from that liquid to solute. And so the solute particles get in the way of the water molecules forming those ice crystals. And so more energy needs to be removed in order to get to that solid structure. And so needing to remove more energy, that means the freezing point is going to be lower than if we had just pure water. So examples of this, we add salt to roads in the winter because that saltwater solution will freeze at a lower temperature than pure water. And so that means it can get colder without ice freezing on the roads. Another example is antifreeze, which is an additive that you put into your vehicle, and it allows for car engines to operate at sub-freezing temperatures when added to the coolant by preventing that coolant solution from freezing. And so again, with it, if we think back to these solids, solid, liquid, gas, if I have pieces of, or if I have other particles that are in here, in order to get those bonds to form, those bonds are having to form around other things. And so the temperature is going to go down for the freezing point because they have to work around these other pieces. The opposite then is true for boiling point. So for boiling point, we're going from liquid to gas. And so with that boiling point elevation, a similar picture to the one before, now if we have pure water, you've got these molecules going from a liquid state to a gas state. Now, as that's trying to happen, we have molecules for a solution that are getting in the way, and it's going to need more energy in order for our liquid molecules to go to gas. So boiling point elevation, the boiling point temperature is going to go up, elevate, for a solution. And so the boiling point of a solution is higher than the boiling point of the pure solvent. And why does this happen? More energy needs to be added to the solution for it to go from those liquid to gas state. Those solute particles get in the way of those liquid water molecules getting released. Those particles being in the way mean there's a lower vapor pressure. And again, you need to put more heat energy in to go from a gas, or to go from a liquid to a gas state. Examples: salt is added to water when cooking because saltwater solution boils at a higher temperature than pure water. And so that water boiling at a higher temperature means the food cooks faster. This really has a fairly minimal impact, mostly because we're not adding so much salt to our pasta water. So really we add it more for flavor, but that's an additional benefit. And that's actually something that is recommended when you are cooking at higher altitudes, because then you're going to have your water boiling at a higher temperature for cooking. And then coolant, that ethylene glycol, just like colligative properties contribute to us having solutions in our car that aren't going to freeze, that boiling point elevation as well, that coolant, ethylene glycol, helps the engines not to overheat in the summer by making it so you're not getting at those boiling temperatures for those solutions that are in your car. So how do we go through and calculate this? So in order to calculate, well, what is that change? That change in temperature, it could be a delta T for your freezing point. It could be delta T change in temperature for boiling point. It just depends on the problem, but our formula is the same. And so in order to calculate what is the change in that temperature, either freezing point or boiling point temperature, which is in degrees Celsius, we need a couple of things. K is going to be a constant that's based on our solvent. So this talks about how much energy is needed for that freezing or boiling. That's a constant for whatever solvent you have. We also need to know molality, lowercase m. And from our formula sheet, remember, molality is moles of solute divided by kilograms of solvent. And then we also need to know I, which is the Van 't Hoff factor, which is the number of particles our solute is going to dissociate into. So when we were talking about how that lithium sulfate and sodium chloride broke up, we were talking about those I values. And all this is provided for you. Those constants are also provided for you. If we look at our formula sheet, our colligative property formula is down here in the bottom left. We also have this table, and on the table, it's giving us the normal freezing points for a selection of solvents. It's also giving us the K values for that solvent for freezing, KF freezing. And then we are also given normal boiling points and then Kb for those solvents as well. And so those K values we are going to get from our table. And for that I as well, if you forget, we have what I means, that is your Van 't Hoff factor, and then capital T is temperature. So capital T is temperature, K value comes from here. That lowercase m, molality, our molality formula is also provided here for us. So we kind of have everything that we need on that formula sheet. So let's just talk about determining our Van 't Hoff factor. We have talked about this with our soluble ionic compounds. We haven't really talked about what happens with covalent compounds much. So our solute disassociates into ions when dissolved if it is ionic, meaning it's going to break into 2 or more particles. So our examples, that sodium chloride is going to break into Na+1 and Cl-1. So that's going to have a Van 't Hoff factor of 2. MgCl2, well, this would break into a magnesium +2, chlorine -1, but we have 2 chlorines, so chlorine -1, so that would have an I value or a Van 't Hoff factor of 3. Aluminum hydroxide, well, this is our aluminum +3, and then we have 3 OHs. So if you want, we can just also look at these. We've got 1 + 3 for those 3 hydroxides, so that's going to have a total of 4 for our I value. And again, those colligative properties, we don't care what this is, we care how many pieces it breaks into. So for our ionic compounds, we are going to find I looking at how many ions total you have. For something that is covalent though, your solute, it might dissolve, but it is going to remain intact. Meaning anytime you have something covalent, you are going to just have 1 particle. So if we look at sugar, C6H12O6, that is not going to break into ions, and so it is going to have an I value of 1. If you are looking at sketching a covalent compound and how is it dissolving, those are going to dissolve in water, but they're going to stay full molecules, and so it is just going to be 1 piece that is, or 1 particle that we have. If we look at ethylene glycol, C2H6O2, well, that is also going to have an I value of 1 because it is covalent. And a reminder, you can tell if something is covalent when you have all nonmetals. All right, so here's our constants table. Here's our formula. They're on your formula sheet as well. So let's go ahead and look at how can we calculate a new freezing or boiling point with that. And we're going to then have to look at it if our change in temperature is a boiling point problem, that means that the temperature is going to go up. If it is a freezing point problem, that means our temperature is going to go down, like that. All right, example 1. Determine the new freezing point. So this one is a freezing problem. And so freezing point depression, that freezing point is going to go down. If 85 grams of lithium phosphate has been dissolved in 250 grams of water. So we need to use that chart of constants. We can go to our formula, because if we're going to find, well, what is the new freezing point? Let's find what is the change in temperature for that freezing point. And that delta T is going to be K times M times I. And because this is a freezing point problem, it is going to be KF. So where do we get this information? Well, my KF is coming from my chart of constants, but I need to know for that K value, that is for our solvent, so what is doing the dissolving? And so we are looking at here, my lithium phosphate has been dissolved in water. So that means that water is my solvent, my lithium phosphate is my solute. And so that K value, KF, that is going to be for our water because that is our solvent. Our molality is for our whole solution. Our I value, that I value is for the solute, which in this case is that lithium phosphate. And so as we go through and kind of look at what are the pieces we need, delta T F freezing is going to be that KF. So that's for water. So I'm going to go to my chart and my KF for water. Water is here. My KF value, 1.858 is there. Now I'm going to have to find the molality. So let's find the molality of our solution. So molality, that lowercase m, looking at our formula sheet, molality is moles of solute over mass of solvent, and we need that in kilograms. So as I'm looking at this calculation, well, moles of solute, I have 85 grams of lithium phosphate. I need to find how many moles that is. And so I'm going to, before I can even use this formula, I need to first do grams of lithium phosphate to moles of my solute, which means we need to know what the molar mass is. So let's write what is our formula for that lithium phosphate. So lithium phosphate, lithium is a +1, phosphate, PO4, is a -3, which means we get Li3PO4. And so I can do my grams to moles conversion now. So we have 85.0 grams of Li3PO4. To get rid of grams, I know that the number of grams of lithium phosphate that are in 1 mole of lithium phosphate is the molar mass. And so I'm going to go to my periodic table and get the molar mass, which is 115.79. When I go ahead and do that, I get 0.734 moles of lithium phosphate. And so that is going to be what gets plugged in to the top part of my formula. I also need the mass of my solvent. So finding the mass of our solvent in kilograms, that's going to be my step 2. Well, my solvent is water. I have 250 grams of water. 250.0 grams to kilograms, I am going to divide by 1,000. If you want, you can just move the decimal 3, or I can show my work with my conversion factor. I know that 1 kilogram is 1,000 grams. 1,000 grams goes on the bottom so that the grams unit cancels, and I'm left with 0.2500 kilograms of water. And now that value is what I can plug in for my mass of the solvent. So now I can find that molality using that information. So my molality equals mass of the moles of the solute, 0.734 moles, divided by 0.2500 kilograms, and I get 2.94 lowercase m molality. And now that is what I can plug in to my formula. All right, so we found that part. 2.94 molal there. And now we just need to find what is our I value for our solute. Well, my solute is lithium phosphate, so that Li3PO4, well, that's going to break into 3 pieces of lithium, 1 phosphate, so that's going to be a total of 4 for our I value, and that's going to go there. So now I found everything for my delta T formula, and I can go ahead and calculate that. So delta T is going to be 1.858 times 2.94 times 4. Plugging that into the calculator, I get 21.85. I'm going to have, looking at my sig figs, this is 4 sig figs. This is 3 sig figs. Our I doesn't have sig figs, so we're going to want 3 sig figs. So 21.9 degrees Celsius is the change in temperature of our freezing point. And so because this is a freezing point example, that means the change in temperature for freezing point is always going to go down. And so we need to take this freezing point and subtract it from our normal freezing point for water. Going back up, water is here. The normal freezing point of water is 0 degrees Celsius. And so we're going to take that normal freezing point of water, so 0.00 degrees Celsius. We're going to subtract off that 21.9 degrees Celsius. And so then we are going to get negative 21.9 degrees Celsius. That is the new freezing point for that solution. And so when we are looking at a freezing point depression problem, we always take the freezing point of our solvent and we subtract minus your delta T freezing. So 21.9 degrees lower than normal. All right, so we are combining things we've done. This is from our notes from the beginning of the unit and combining those in here. So it is kind of a lot of work, but using your formula sheet and those things that you know. All right, example 2. Determine the new boiling point if 5 grams of calcium chloride have been dissolved in 50 grams of water. So now with that boiling point elevation, that means our boiling point is going to go up. Down here, we did the freezing point of our solvent minus that delta T. For boiling point, our last part is going to be to take the boiling point of our solvent, and instead of subtracting, we're going to add that delta T boiling to it to find the new new boiling point temperature with that. So that's the only change, and we also have to make sure we're grabbing the correct constant. So if in order to do this, we have to go back to that original formula. Our delta T is going to equal K times M times I. K is for our solvent, and that comes from the chart. So our solvent, this is going to be dissolved in 50 grams of water. And we are doing boiling, so we're going to need that KB. And so I can go and get that from my chart. Water, KB is 0.512. My molality, that is for my whole solution. I need to calculate that. And so I can go ahead and do that over here. So that molality is going to be our moles of solute over kilograms of solvent. And then our I value is going to come from for our solute, how many pieces is that breaking up into? So CaCl2 is our solute. That's how much is getting dissolved. So that calcium chloride, CaCl2, that's going to be 1 calcium ion. 2 chlorine minus 1 ions, so that's giving us an I of 3. So I'm going to calculate my molality, but I know my value of 3 is coming from the ions that is breaking up into. All right, let's do our molality. If you want, go ahead and do this on your own. Moles of solute, we need to first go from grams of CaCl2 to moles of CaCl2, so that's a one-step molar conversion. 5.0 grams of CaCl2. We've got grams of CaCl2 on the bottom, 1 mole of CaCl2, and our molar mass is 110.98, which gives me 0.045 moles of that calcium chloride. I also need to find my kilograms of solvent. My solvent is water, so we're going from grams of water to kilograms. So we've got 50.0 grams. We know that there are 1,000 grams in 1 kilogram. And so that's going to be 0.0500 kilograms of water. I maintained sig figs on both of those. You can kind of keep more sig figs till the very end of this calculation, but I did make sure to keep my 3 sig figs here that I needed, so that when I go and do this calculation, I'm still maintaining those. So my molality is going to be that 0.045 moles over 0.0500 kilograms, and we get 0.90 molal from that. And we are, you can keep that answer, or if you want, you can round it to sig figs after finding your molality, as long as I can see your work. And then that 0.090 is our molality. That's what is going to go into our formula here. And then we multiply. So that 0.512 times 0.90 times 3. And as I'm looking at this, we've got our, we've got delta T is going to be 1.41 degrees Celsius, which as I look at this, we would have, this is 2 sig figs, this is 3 sig figs. So let's go 1.4 degrees Celsius. And now to find, well, what is our new boiling point? Because that's just the change in the boiling point temperature, delta T boiling. We're going to take now what is the normal boiling point of the solvent. We can go back to our formula. Normal boiling point of water is 100 degrees. So we're going to have 100.00 degrees Celsius plus 1.4 degrees Celsius. And so we're going to get 101.4 degrees Celsius is that new boiling point for water. So the changes from boiling to melting are just in this final step of adding, if it is a boiling point elevation, or subtracting if it is a freezing point depression, and also in just making sure you're using the correct constants from that table. I have the answers for the next problem here if you would like to look at that. My answer is reflected at the bottom. One thing to note, we are using naphthalene as our solvent, and so that naphthalene solvent, K value is there. We also then need, that's our normal freezing point of naphthalene, so we are then subtracting off our delta T value from that. Also, we are dissolving benzene. Benzene is your solute, and benzene is going to have an I of 1 because it is covalent, so it will not break up into ions. Reach out to your teacher with any questions.